Welcome back to the deep dive. Today we're taking you on, well, an extraordinary journey, one that really pushes the boundaries of imagination and physics. But before we plunge in, there's a really crucial note. This whole deep dive, it springs from a truly speculative conversation. It was between a curious mind, Vince, and an AI, ChatGPT. So while we're about to explore some pretty mind-bending concepts, just remember, we are firmly in the realm of theoretical physics here and, highly conceptual engineering. Today we're unpacking an idea that sounds straight out of science fiction, like really out there. A device that can convert all forms of electromagnetic radiation into usable electricity. And trust me, it gets even wilder. It leads us to think about, well, the implications of harnessing energy from something as exotic as an artificial black hole.
It's a fascinating thought experiment, no doubt about it. We'll explore how such a universal energy harvester might actually work, theoretically, and what it means for everything from, say, deep space travel to maybe power grids here on Earth. And then, yeah, as you said, we'll go off the deep end a bit. Consider an energy source that really redefines power generation.
So if you're ready to explore the ultimate in clean, compact, and frankly mind-bending energy solutions, settle in. This is going to be an illuminating deep dive. Okay, let's unpack this universal energy harvester. So the basic idea, a device that absorbs everything on the EM spectrum.
Pretty much, yeah. From low-frequency radio waves all the way up to high-frequency gamma rays, and converts it all to electricity.
How would something like that even begin to work? I mean, what kind of structure are we talking about?
Well, the key thing is the sheer breadth of that spectrum. It's huge. So you wouldn't use just one material. It would have to be a modular surface built with incredibly tunable layers. Think of it like a sandwich, but nanostructured, highly layered, super thin metasurfaces, thin films, semiconductors, conductive meshes, all stacked up.
Ah, okay. So not just one flat panel, different layers for different jobs.
Exactly. Each layer specializes.
So like the top layers, what are they grabbing?
Right, the top layers. They need to be transparent to visible light, mostly, but optimized for the high-energy stuff. UV, X-rays, gamma rays. You'd use materials with a high atomic number, IZ materials, we call them. They're good at triggering things like the photoelectric effect or Compton scattering, basically ways to knock energy out of those photons.
Got it. And then moving down through this sandwich, what about visible light, infrared, the stuff we're more familiar with?
Yeah, the middle layers, that's where you'd have semiconductor structures, tuned specifically for visible light, infrared, near UV. It's actually pretty similar to the advanced multi-junction solar cells we have now. Those already try to capture different colors, different wavelengths of sunlight.
Okay, that makes sense. And then the bottom layers, for the really long wavelengths.
Down at the bottom, you'd need something different again. Antenna-like metamaterials, maybe? Or even superconducting coils. Those structures are designed to grab the low-frequency EM radiation. Radio waves, microwaves. Kind of like how your radio antenna works, but way more sophisticated.
And I assume each layer uses a totally different method to convert that energy into electricity.
That's right, it has to. You'd have photovoltaics for visible and near-infrared, standard solar cell stuff. For thermal radiation, that far infrared heat, you might use thermophotovoltaics, TPVs, or maybe pyroelectrics. Radio and microwaves, that would likely be antenna-coupled rectifiers. We call them rectennas. And for the really energetic photons, the X-rays and gamma rays, you're looking at things like scintillators paired with photodiodes, or maybe direct semiconductor absorption, just converting that punch directly into a signal. And coordinating all of this, you need something smart at the core, a kind of quantum hybrid control unit to manage the energy flow, balance the load.
Wow, that sounds incredibly complex. How does it possibly adapt? Say if it moves from bright sunlight into, I don't know, deep space with just faint cosmic background radiation.
Yeah, that's the kicker. For it to be truly efficient, it can't just be passive. It would have to be smart. It'd likely use advanced AI algorithms to dynamically tune its surface properties in real time.
Like a chameleon.
Sort of. Like a smart skin, exactly. It could reconfigure its nanostructures, maybe using tiny micromachines, MEMS, or phase change materials to shift their properties. So it could optimize itself, whether it's facing a microwave tower, or sunlight, or just picking up cosmic rays, constantly adapting.
Okay, but converting high-energy stuff, especially gamma rays,
Right.
that generates heat, right? A lot of heat. How does something so thin avoid melting?
Cooling is absolutely critical. Yeah, you'd need a serious system. It can involve passive radiative cooling layers, maybe inspired by nature, like those desert plants that are amazing at shedding heat at night. And potentially, you might even need superconducting conduits to move the electricity around with almost zero loss. But then you'd need cooling for those, maybe cryogenic fluids or advanced phase change materials.
So conceptually, what does it look like?
You can imagine it as um, a sleek black panel, subtly curved, maybe shimmering slightly because of all the microtextures on the surface. Paper thin, but really rugged. And scalable, you could have one phone-sized, or cover the entire hull of a satellite, with ports or wireless systems to get the electricity out, of course.
The applications just seem huge.
Yeah.
Powering spacecraft just from background radiation in deep space.
Yeah.
Deploying them in ocean trenches.
Anywhere there's EM radiation, yeah. But think about Earth, too.
Right. Cities.
Exactly. Clean energy in cities. Imagine buildings covered in this stuff, silently collecting ambient radio waves, microwaves from towers, infrared heat, sunlight. It's not just a solar panel. It's more like an energy umbrella, collecting energy across the whole spectrum, day and night. Weather doesn't matter as much.
Okay, this is where my mind started buzzing. You mentioned infrared absorption, heat.
Yeah.
So if I reached out and touched this panel, would it actually feel cold because it's sucking the heat, the infrared, right out of my hand?
That's a really sharp question. And yeah, it very well might. It's a cool thought, isn't it? When you touch anything, you exchange heat, mostly infrared radiation and direct conduction. Now, if this panel is actively designed to gobble up infrared, especially the wavelengths your body emits, that's around 9 to 10 microns, it would draw heat from your hand much, much faster than a normal object.
So I'd perceive it as cold, like touching metal versus wood, even if they're the same temperature.
Exactly like that. The metal feels colder because it conducts heat away faster. This panel would be doing something similar, but by actively absorbing the radiation.
So physically, it would have really low emissivity. It doesn't radiate much heat back at you, but super high absorptivity for infrared. It's just greedy for heat.
That's the idea, precisely. Greedily sucking up the IR.
Could it actually get objectively cold, though? Colder than the air around it?
Yes, potentially. If it's really good at radiative cooling, beaming its own heat away, maybe into space, or if it's in an environment where it can offload energy faster than it gains it, think deep space, or just very cold air. The surface itself might actually drop below the ambient temperature.
And with those adaptive nanostructures you talked about, could it be a smart surface? Like it senses my touch and dials back the IR absorption so it doesn't feel freezing or cause frostbite.
Yeah, that's a wild, futuristic possibility, a surface that reacts to you. But here's maybe an even more elegant idea. The panel could use that infrared conversion ability to cool itself.
Wait, what? So it doesn't just radiate waste heat away. It converts its own heat into more electricity.
You got it. An electrothermodynamic self-cooling system. Sounds fancy, but the idea is simple.
How does that work?
Well, everything above absolute zero emits infrared radiation, right, including the panel itself as it operates. If the panel can capture its own outgoing infrared radiation and convert that energy into electricity instead of just letting it radiate away, it's effectively lowering its own internal energy as temperature drops.
So it's not just dissipating heat, it's harvesting it. That's like thermodynamic judo, as you said, turning waste heat into power.
Exactly. A thermodynamic judo move. It makes a liability waste heat into an asset. More power and built-in cooling.
That dual function, wow, that's huge for spacecraft. Thermal management is always a nightmare up there.
Absolutely critical. And imagine it on Earth. Absorbing waste heat from hot pavement or machinery. Staying cool and generating electricity. You could even get a tiny trickle of power at night just from converting its own emitted infrared as it cools down.
How would you design for that specifically?
You might use IR transparent top coatings so the internal heat can get to the conversion layers easily. Maybe photonic crystals, special nanostructures to help radiate heat efficiently in specific wavelengths that escape the atmosphere easily. Thermal diodes, nano antennas, directing that outgoing heat into the energy conversion pathways.
Okay, let's take this panel to deep space. An interstellar craft. This thing could be everything, right? Power source, radiation shield, thermal regulator, all in one passive system.
Potentially, yeah. A truly multifunctional skin for the ship. But what's the energy environment like out there? Let's say 2 light years from the nearest star, middle of nowhere.
What's available?
Not much, really. Starlight is negligible.
Yeah.
Your main sources are the cosmic microwave background, that's CMB. That's like a faint, cold microwave glow everywhere, about 2.7 Kelvin. Then you have high-energy cosmic rays and gamma rays. Those are sporadic. They come from specific directions, but they pack a punch when they hit. And, of course, the ship's own waste heat. Its infrared signature.
Neutrinos.
Useless for energy. They just zip right through almost everything.
So even with this amazing panel, the actual power you could collect passively in deep space is going to be tiny, isn't it?
Extremely low, yeah. Let's run some rough numbers. The CMB flux is only about 0.25 watts per square meter. If you're lucky, maybe 10–20% efficiency. So you're getting maybe 0.025 to 0.05 watts per square meter, tiny. Cosmic rays and gamma rays. The flux is low, maybe 1 particle per square centimeter per second, but they're high energy. Conservatively, maybe you could pull 0.1 to 0.5 watts per square meter from those hits. Distant starlight, galactic background, negligible. Maybe 0.01 watts per square meter, if that.
So total passive harvest.
Right.
We're talking maybe 0.1 to 0.6 watts per square meter compared to like 1,000 watts near Earth.
Exactly. It's incredibly energy poor out there. Really puts the challenge of interstellar travel into perspective.
But there's a silver lining, right? The radiation shielding.
Absolutely. Those same high-Z materials and layered structures designed to absorb high-energy gamma rays and X-rays will naturally block or scatter them too. And the fact that it converts them to electricity is even better. It turns harmful radiation into useful power, lowering the dose inside the ship. A fantastic two-for-one deal.
And thermal regulation too. Space is cold, but the ship makes heat.
Right. So the panel captures the ship's own waste infrared, recycles it into power, and it can also be designed to radiate excess heat away in controlled ways, maybe using those atmospheric windows we talked about to keep the ship's temperature stable. Multifunctional, like we said.
Okay, time to go properly off the deep end. As promised, let's imagine, just imagine, we could create an artificial singularity. A micro black hole, say the mass of a bowling ball, about 7.3 kilograms, and we suspend it magnetically in a vacuum and surround it completely with our universal energy harvesting panels. What happens then? What about Hawking radiation?
Okay, yeah. Now we're deep in speculative territory, based on that Vince ChatGPT concept. A 7.26 kilogram black hole. It would be unbelievably small. Its event horizon, the Schwarzschild radius, would be about 10 to the minus 26 meters. Way, way smaller than a proton. But the energy output? Through Hawking radiation, it's astronomical, about 5.3 times 10 to the 14 watts.
Wait, 10 to the 14, that's 530 trillion watts.
Yep, over 500 trillion watts. That is nearly 40,000 times the entire energy consumption of Earth, from something the mass of a bowling ball.
That's insane, and it's pure electromagnetic radiation.
Mostly, because it would be incredibly hot. The Hawking temperature is estimated around 1.8 times 10 to the 23 Kelvin. It's an absurdly hot gamma ray oven, as you put it, spewing out gamma rays, X-rays, hard UV.
So if our panels could surround that, and let's say they're really good, maybe 70% efficient at converting all that high energy radiation.
Then the usable power would still be enormous, around 3.7 times 10 to the 14 watts, 370 terawatts. Sustained, compact, clean power.
Theoretically. But what about feeding it? Does adding mass change things, like dropping dust or gas into it?
Ah, yes. Feeding it makes it even more interesting, and potentially more powerful. When matter falls into a black hole, before it crosses the event horizon, a chunk of its rest mass energy gets radiated away. About 6% for a simple, non-rotating black hole. So you fed it, say, 1 kilogram of matter per second. That process alone would generate about 5.4 times 10 to the 15 watts.
That's 10 times more than the Hawking radiation.
Exactly, and it scales with how fast you feed it. So by feeding it, you turn the black hole into a true mass-to-energy reactor. The panels would just absorb all that intense radiation from the infalling matter, the accretion disk.
So the panels handle everything. Thermal regulation, shielding. They just absorb all the gamma rays, X-rays.
Pretty much everything that comes out. Any unconverted energy could maybe be radiated away through specific IR channels. The system could even potentially self-cool using a kind of Hawking feedback loop, absorbing and converting its own excess internal radiation. Really is this concept of a contained artificial black hole reactor, a tiny star running on quantum decay instead of fusion.
Now, something counterintuitive about Hawking radiation, smaller black holes are hotter, right? They radiate more.
That's exactly right, and it surprises a lot of people. As a black hole loses mass, its Hawking radiation gets more intense. Hotter temperature, higher energy photons, more power output. The temperature is inversely proportional to the mass. The power output is inversely proportional to the mass squared.
So it's a runaway process. Smaller means hotter, means radiates faster, means gets smaller even faster.
Precisely. Left alone, it evaporates faster and faster, ending in a final burst.
Which means, for our hypothetical reactor, feeding it isn't just for extra power, it's essential to keep it stable, to control the output.
Absolutely crucial. A constant mass feed stabilizes the black hole's mass and keeps the power output steady. If you wanted more power, you could temporarily reduce the mass, but that shortens its lifespan. It could become a sort of high-energy burst source if you manipulated the feeding.
Okay, let's scale this up. Powering a truly huge interstellar ship, 10 miles long, maybe, with, say, 5 spinning rings for gravity, each half mile wide, 3 miles in diameter. That needs a lot of power. Let's say 100 gigawatts usable electricity.
Right. For 100 gigawatts usable, assuming our 70% panel efficiency, the black hole itself would need to radiate about 143 gigawatts total.
What mass black hole produces that much Hawking radiation? Still bowling ball size.
Oh no, much bigger.
Yeah.
To get down to that relatively low output of 143 GW, the black hole needs to be much more massive, about 50 billion kilograms.
50 billion kilos. That's the mass of a small asteroid.
Exactly, a small asteroid mass black hole.
And to keep that output steady within, say, plus or minus 10%, how much mass do we need to feed it per second to counteract the Hawking radiation loss?
Let's see. To balance out 143 GW of energy loss via EMCMC, the required feed rate is incredibly small, about 1.6 grams per second.
1.6 grams. That's it. That's like a spoonful of matter every minute, powering a city-sized starship.
It highlights the insane energy density we're talking about. EMC is no joke.
Could you even use the Hawking radiation itself for propulsion?
Theoretically, yes. If you could somehow perfectly collimate, like focus a fraction of that radiation into a beam, say 10 to 50% of the raw power, that 14.3 to 71.5 gigawatts of directed energy would produce thrust, about 48 to 238 newtons.
That doesn't sound like much thrust for a giant ship.
It's not much push at any given moment, no.
Yeah.
But it's constant and incredibly efficient because you're essentially using pure energy for propellant. Over months or years, that gentle, constant push adds up to enormous velocities for interstellar travel, a photon drive, basically.
And those 5 big rings on the ship, that changes the surface area cooling needs, maybe?
Definitely. 5 rings, half-mile wide, 3-mile diameter. That's a lot of surface area, roughly 61 million square meters. So cooling and shielding calculations get more complex. But the core power requirement, the 100 gigaW from the Singularity, that stays the same, unless the rings themselves need extra power.
Okay, let's step back from the Starship design for a sec. How on Earth, or maybe off Earth, do you actually create one of these micro black holes? This feels like the biggest hurdle by far.
Oh, it's way, way beyond current technology, pure speculation territory, theoretically.
Yeah.
You need to compress an unbelievable amount of energy or mass into that tiny, tiny volume, the Schwarzschild radius we talked about, smaller than a proton.
Lasers? Particle colliders?
Maybe. High-energy particle colliders are the closest thing we have, but they fall short by many, many orders of magnitude. Spherical laser implosion, like they try for fusion, but scaled up unimaginably, perhaps. Or maybe some kind of quantum gravity engineering we can't even conceive of yet.
The challenges just seem insurmountable. The energy needed is like converting a mountain into pure energy, the precision required for the compression. And we don't even fully understand quantum gravity yet.
You've nailed the problems. Plus, what holds it together once formed, besides its own gravity? How do you contain it? No known material could do it. Maybe magnetic fields if it's charged? Suspending it in a vacuum? A slightly more realistic sci-fi idea might be finding and capturing primordial black holes left over from the Big Bang, if they even exist.
Or pure sci-fi concepts, dimensional shenanigans.
Right. Dimensional collapse, siphoning energy from somewhere else, artificial gravity wells, stable exotic matter. Who knows?
So time frame estimate, if it's even possible.
For creating micro black holes, maybe 250 to 500 years plus, if ever. Then you need stabilization, containment, maybe another 100 years after that, energy harvesting, another century. It might just never happen.
Okay. Let's swing back to the slightly more plausible part. The electromagnetic voltaic panel itself, especially one designed for that Hawking radiation furnace. How do we build that?
Right. Still incredibly advanced, but maybe more grounded in physics we sort of understand. It's a radical form of high-energy harvesting. First, you have to define the energy spectrum. Hawking radiation from a small black hole is mostly high-energy gamma rays, maybe electron-positron pairs too, so the panel needs to handle May to GeV range energies and survive.
So it's not just layers like the first version, it needs to handle particles too.
Exactly. It's more complex. You'd need maybe a gamma photon absorber layer first, dense stuff, tungsten, lead glass, something to force those gamma rays to undergo pair production, turn into an electron and a positron.
Okay, now you have charged particles.
Yep. So next, a pair extraction layer. Powerful electromagnetic fields, like in a particle accelerator, to grab those electrons and positrons, separate them, channel them.
And then harvest their energy.
Right. A charged particle energy conversion layer. Maybe using MHD magnetohydrodynamics, extracting energy from moving charged fluids or plasma, or advanced thermoelectric layers that convert kinetic energy directly. And finally, a thermal recovery layer. Anything left over, any waste heat, gets absorbed and converted using high-temperature TPVs or thermoelectric generators. Got to catch every bit of energy.
And you'd still need that magnetic containment shell around the singularity itself, right? To channel the radiation.
Probably, yes. A magnetic bottle or something similar to direct the onslaught onto the panels
Yeah.
and the materials. You'd need futuristic stuff.
Right.
Graphene composites, maybe room temperature superconductors if they ever become real radiation-hardened quantum materials.
Plus the AI control system we talked about earlier.
Absolutely essential. Real-time analysis of the particle flux, constantly adjusting the fields, the cooling, the feed rate, preventing overload, keeping it stable, and handling the output. Multi-stage transformers, maybe storing energy in field-based capacitors or plasma batteries, distributing it with superconducting lines.
So this panel, it's not a solar cell at all. It's like a particle collector, a plasma converter, a radiation harvester, all rolled into one complex shell.
That's a good way to put it. A hybrid energy conversion shell.
What about time frames for this technology? More realistic.
Much more realistic, relatively speaking. Multi-band panels covering light and infrared. We're already working on the basics. Maybe 10, 30 years for advanced versions. Getting good at X-ray and gamma conversion, that's harder. Maybe 50, 100 years. Full spectrum EM harvesting, really covering everything efficiently, perhaps 100 and 150 years. Integrated radiation shielding could come along in 50, 100 years too. Still long timelines, but not necessarily millennia.
So putting it all together, the Starship powered by a singularity reactor wrapped in these advanced panels, minimum time frame, best guess.
Minimum if everything clicks. Maybe 300, 500 years. More realistically, assuming steady progress, a big space industry, breakthroughs in quantum fields, probably closer to 800 to 1,000 years. It's a long-term vision.
Who's working on the building blocks today, though? Any real-world connections?
Oh yeah, definitely. For the all-spectrum panels, research into thermophotovoltaics is happening at places like MIT, NREL, Stanford. Multi-junction solar cells are pushed by NASA, Solero, rectennas for microwave ore harvesting at Georgia Tech, Berkeley, quantum dots, metamaterials. Lots of labs are working on tailoring light absorption.
And the singularity side, besides theory.
Mostly theory and tangential experiments. Hawking's original work, of course. CERN's LHC looks for micro-black holes, hasn't found any. People simulate Hawking radiation using analog systems, Bose-Einstein condensates, water waves. NASA and CERN study matter-antimatter annihilation, which is another super energy-dense process.
So the building blocks are being explored even if the final structure is way off.
Exactly. And NASA ESA, they have advanced propulsion teams looking at powerful energy sources like nuclear and plasma. And NASA's STMD funds work on smart surfaces for thermal control. Progress is happening on many relevant fronts. Primitive versions of some panel tech might appear in 50, 100 years.
Okay, but with technologies this powerful, even centuries away, we have to talk about what could go wrong, the disaster scenarios.
Absolutely crucial to consider. For the singularity itself, the nightmare scenario, though maybe low risk based on current physics, is uncontrolled collapse. It stops evaporating, starts accreting matter, consumes the ship. Maybe worse, a more plausible medium risk, a radiation burst. And instability, maybe containment hiccups, releases intense gamma rays or particle jets, fries everything nearby, annihilates systems, crew, and then containment field failure, or whatever holds it stable, magnetic, gravitational, whatever fails. Instant release of extreme gravity gradients, spaghettification, implosion, detonation, high risk potentially.
And the panel itself isn't risk-free either.
Not at all. Thermal overload is a big one. Stick it too close to a star, a powerful radar weapon.
Yeah.
It absorbs so much energy it melts down, maybe ignites the ship. Medium risk, high risk, unintended EM interference. If it's absorbing everything, it might accidentally jam communications, navigation, scramble nearby electronics just by being there. And runaway energy accumulation. If it collects energy faster than it can safely use, store, or radiate, maybe the cooling fails or the storage overloads, it could release that energy explosively, like a reactor breach. Medium risk.
And if you put them together, the singularity and the panel.
Compound risks. The big one is an energy feedback loop. Panel draws ambient energy, singularity emits more radiation, panel absorbs that, maybe gets hotter or overloads, causes instability in the singularity. Runaway meltdown, maybe disintegration. High risk without absolutely perfect control. And the really, really out there risk, capping into the fabric of spacetime itself. If manipulating a singularity messes with the vacuum energy state, could it trigger vacuum decay? A phase change in the universe itself. Hugely speculative, but the ultimate potential disaster.
So mitigation would have to be incredibly robust. AI watching for collapse, ejection systems to jettison the core.
Exactly. Quantum field containment, predictive AI, fail-safe ejection into deep space, massive energy dumping systems operating far from inhabited zones, backup analog controls, layers upon layers of safety, mostly theoretical themselves.
Wow. Okay. From a panel that feels cold because it's literally drinking your body heat
Yeah.
to an asteroid mass black hole powering a starship, this has been quite the journey, an exhilarating trip to the edge.
It really has, and it shows how even these really far-out theoretical ideas connect back to actual research happening now. TPVs, metamaterials, understanding extreme physics, they're all small steps on potentially very long roads, roads that could reshape everything. But also, as we saw, roads with potential dangers we need to think about very carefully.
Absolutely. A powerful reminder that with great power comes great responsibility and the need to understand the implications. So reflecting on all this, what stands out most to you? What's the next frontier you find yourself wondering about, especially when we start combining these wild ideas? We really hope this deep dive into universal energy harvesting and artificial singularities has, well, stretched your mind a bit, left you thinking about the incredible possibilities, but also the critical considerations that lie ahead in our future. Until next time, keep exploring.